One of the first things people ask when they hear about quantum computers is, what makes quantum computers so different? Almost every pop science article will have a bad answer to this question, but that's actually not really because of the articles being bad, but because the question is surprisingly subtle. Like, I watched one of my coworkers defending their PhD in quantum computing, and the last question they were asked during their defense was, what makes quantum computers more powerful? And they didn't have a good answer. But the people asking the question also didn't have a good answer. There was a bit of discussion, no real consensus. They just had to leave it and move on. Basically, even experts in the field don't have a good answer to this question. Now, usually answers to how are quantum computers different focus on the details of quantum mechanics, like entanglement and interference. They focus on how quantum computers work. But that's not really appropriate for someone just hearing about quantum computers for the first time. In this video, I want to be more direct. I want to address a slightly different question. I want to focus on a thing a quantum computer can do without really going into why it can do it. And then I want to show how that thing could be useful. Basically, I want to give you the flavor of what makes a quantum computation different instead of a recipe for doing a quantum computation. Now, in order to do that, I do have to explain an example. But here's the simplest example I could come up with. What you're seeing on screen is a logic circuit. This logic circuit takes two inputs. Each input is a bit. It can be true or false. And the circuit also produces two outputs, and the outputs are also bits. They're also going to be true or false. The top output is just the same as the top input, whereas the bottom output is computed from both inputs. It's computed using what's called a XOR gate, which just tells you if the two inputs are different. So if the two inputs are different, like one is false and one is true, the bottom output will be true. If the two inputs are equal, the bottom output will be false. I hope that makes sense. If you've never seen a logic circuit before, that might be a lot very fast, but this is at least a very simple logic circuit. Now, a very important property of this particular circuit is that the data dependence goes one way. The bottom depends on the top, but the top doesn't depend on the bottom. You can't change the top output by changing the bottom input. Actually, I would say this is basically the Platonic ideal of a one-way effect. And this is still true if you put other stuff around the circuit. No matter what preparations you put before the circuit or what cleanup you do afterwards, you can't switch the direction of the data dependence as long as those additional operations don't interact the top and the bottom. There's no way you can take data dependence in one direction and flip it to go in the other direction using local operations. It's impossible. For bits, if the circuit is operating on qubits instead of bits, the story changes. There's a quantum operation called the Hadamard Operation, which you can apply to any qubit. And if you completely surround the circuit with Hadamard operations, it flips the direction of the data dependence. The first time I saw this, it blew my mind. Like, this is basically reversing cause and effect. This is walking past a light switch to the light bulb, somehow flicking the light bulb as if it were a switch, and seeing the switch light up as if it were a light bulb. It doesn't make any sense, but it's really how it works. Now, you might think that in order to reverse cause and effect, you would need quite the fancy operation. This Hadamard thing must be crazy complicated. But actually, it's a totally trivial operation. If you were storing your qubits in the polarization of light, for example, then the Hadamard operation corresponds to reflecting the direction of polarization through an angle. You can buy pieces of quartz that just do this. It's not complicated. It's a totally normal operation. What's actually going on is that in quantum mechanics, our simple little XORing operation isn't quite as simple anymore. It has the effects you expect, but it also has additional effects. These additional effects are often called the kickback of the operation. Basically, the operation ends up having a dual nature, where from one perspective, the data dependence goes one way, and from another perspective, it goes the other. That makes it sound a bit like the expected effects and kickback effects are fighting each other, but actually they're two sides of the same coin. It's just the case that in quantum mechanics, when you set up a situation where one thing affects another, that is equivalent to setting up a situation where the effects go in the other direction. Fundamentally, this is why it's not possible to measure a quantum thing without changing it. Setting up a measuring device is setting up a data dependence, where the state of the quantum thing will affect the state of the measuring device. And in quantum mechanics, any such dependence will unavoidably have a kickback effect, where, from a different perspective, the measuring device is determining the state of the quantum thing. This isn't because of imprecise control, or because of noise, or because of any imperfection in the measuring device. It's just definitionally how quantum things work. Like, the circuit on the previous slides wasn't a physical object, it was a platonic ideal of one thing affecting another. And even that had kickback. This limitation is deep down, it's in the math. You can't avoid it. But one of the very useful skills you can have in life is to take a limitation like this and turn it around into a strength. Like, suppose someone asks you to go into a room that has a ton of light switches and figure out which switches control a light bulb. So you go to one switch, flick it, see if the light changes, go to the next one, flick that one, see if the light changes, and keep doing that until you run out of switches. In a room with a lot of light switches, it can get pretty tedious. But if this was a quantum system, then the fact that the switches control the light bulb would imply there's a kickback effect, where the light bulb affects the switches. If we could just put Hadamard operations around this whole thing, so to speak, the light bulb would become like a switch, and the switches would become like light bulbs. So instead of trying the switches one by one, you could just go to the bulb and flick the bulb and see which switches lit up. And that would be a lot faster, because there's only one thing to try flicking instead of a bunch. Now, this isn't going to work with real light bulbs, because the context they're in isn't right. For this to work, you need the bulbs and the switches to be isolated from the rest of the world. Basically, the light bulb lighting up the room, interacting with the world, is going to create all kinds of other kickback effects that ruin what we're going for. You really need it to be isolated. But in principle, you could be given a pen and paper problem that acted like this sort of idealized, isolated light switch problem. For example, I could give you a gigantic logic circuit that behaved in this way, where a single output bit depended on the parity of some of the input bits, but you didn't know which ones. And I could purposefully make that circuit really complicated, so it was hard for you to figure out what was going on. Maybe so complicated that you'd have no better option than just running the circuit to see what happened. And the key idea here is that if you're using a normal computer to run the circuit, you'd have to run it multiple times, once for each switch. Whereas if you had a quantum computer, you could just surround the circuit with Hadamards and run it once. That would be enough to figure out all the switches that affected the light bulb. And that's it. That's how you turn the limitation of having a kickback effect into a strength, into a tool. We started with a strategy that would have required many runs of a circuit to solve a problem, but because there was this kickback effect present, we were able to replace that with a strategy that only required one run. That flip the data dependence idea was actually one of the earliest quantum algorithms. Unfortunately, these light bulb type problems that it solves aren't actually very interesting. They don't really matter in the real world. But once people had a foothold on using quantum effects in this way, things kind of escalated. It was realized that you could do more subtle versions of kickback that gave more information, that you could use that information to figure out non-trivial things about circuits, like their period, and that ultimately, these things could be used to solve problems with real-world impact, like factoring numbers. And it all started with kickback. So, returning to the title question, what makes a qubit different from a bit? My answer to this question, which is not a complete answer, but I do think it's a good answer, is that the difference is that qubits have kickback. When you do something with qubits, there are these additional unavoidable effects that are present in the system, And sometimes, just sometimes, those effects are useful.